Okay, it is time for the keynote. It will be given by the Director of Engineering at Skillshare, Samantha Quinones. Keynote talk is actually about pragmatic optimism, how PHP conquered the web. Samantha, can you hear us?
Yes.
Okay, we can hear you loud and clear, and soon we will see you. Now we see you. Hi, how are you doing?
Oh, very well. It's very early here.
Okay, great. Next 45 minutes are yours.
Wonderful.
See you.
Thank you. Todos, good morning. Thank you. I want to first thank the organizers for inviting me to speak with you all today. I hoped that I could have done it in person, but I am very much there in spirit. I'm going to be talking about PHP and its history over the past quarter century, but I hope that you'll forgive me for going about it in kind of a roundabout way. For those of you who aren't familiar with me, my name is Samantha Quinones. I've been around the PHP community for many, many years. You may know me from my Twitter account, where I post a lot of bad jokes about Star Trek, or from some of the talks that I've given over the years about computing history. So this is a topic that is really very close to my heart. The thing is, I'm not really a professional programmer, at least not anymore. It's been years since I wrote a line of code and got paid for it. These days, when I write code, it's almost always part of what I call AI art projects. I was a professional programmer though for 20 years, and I work with and manage them now. But really, it's the last 5 years since I became a hobbyist again that I recovered my love for coding and gained the perspective that I needed to give this talk. I'm going to talk to you about how and why PHP came to dominate web development, why it still drives so much of the content on the web, and how it is, in my opinion, the programming language that best embraces the concept of pragmatic optimism. So to understand where PHP came from, we have to talk about the history of computers. And to understand the history of computers, we have to talk about math. I promise we'll start with something really simple. It's easy to see when we look at all of the most basic algebraic expressions that what we're doing is counting. And in fact, all elementary algebra can be thought of as counting. Addition is counting. Subtraction is counting backwards. Multiplication is counting groups of numbers that you've already counted. Division is doing that backwards. Even when we get into more advanced algebraic expressions like exponents and logarithms, it's all just fancy counting. I'd like to take a moment before I move on to recommend a video. If you're interested in this idea, it's by a mathematician and artist named Vi Hart. It really opened my eyes to thinking about algebra in this way, and it helped me connect with what is really happening inside the computer. After all, a modern computer is a machine that is built to count very, very quickly. So, please check her video out. I find it very, very inspiring and interesting. So with all of that in mind, I want to start our story in France in the year 1642, where a 19-year-old Blaise Pascal was faced with helping his father, the tax collector for the city of Rouen. Calculating taxes owed and paid for the whole city was exhausting and tedious work. And could you imagine managing the taxes for a large city like Rouen with nothing but quill pens and ledger books? Pascal would eventually go on to become one of the most influential mathematicians in history. In fact, he has a programming language named after him. But at this point, he was an overworked teenager with an interesting idea. And he didn't have Vi Hart's YouTube videos, but thankfully he was much, much smarter than me and already understood that arithmetic can be expressed through counting. And so he set about building a machine that could do arithmetic for him. It took him about 3 years and around 50 prototypes, but eventually he received a royal patent for his design and built around 20 of these machines total. They called them Pascalines, and you can see one of the 8 or 9 that are remaining on the screen right now. This device used a series of drums to add numbers directly by counting one by one and then carrying tens to the next drum. It's really hard to visualize, at least it is for me. So if you want a really great demonstration and see this at work, a fellow who goes by Nico71 built a working Pascaline out of Lego Technic bricks. And there's a very, very cool video of him using it to do addition. It's a very, very interesting machine. Half a century later, a fellow named Gottfried Wilhelm Leibniz, who was a philosopher and a mathematician, encountered an ancient Chinese book called the I Ching. And Leibniz had spent a lot of his academic career studying the concept of symbolic thought, the idea that thought and logic can be broken down into computations. Earlier in his career, he had done a lot of work to document the binary number system. It had already been known about and worked with, but he documented and refined the system. And he related the I Ching's concepts of the duality of yin and yang to the ones and zeros. And later on in his life, he would also build mechanical calculators, though these were stepped calculators that were capable of all four of the basic mathematical operations. He also theorized about machines that were capable of even more complex math. He thought about a machine called a calculus rationator that could actually do integrations. He laid a lot of the groundwork that Ada Lovelace and Charles Babbage would expand on in the following century. So Babbage was a mathematician and engineer who spent a lot of his career theorizing and later building mechanical computers. He developed a prototype difference engine that was capable of any arithmetic function, but was specifically designed to compute polynomials. He followed this work with a more theoretical design, which was actually never built. There's a project underway in the UK to actually build an analytic engine. But this was like the first design for a general purpose computer. So a computer that's capable of executing any program. Alan Turing wouldn't be born for another 80 years, but the analytical engine's design is Turing complete. It could run any program, it could compute any possible program. Ada Lovelace, who's a contemporary mathematician, maintained a very long correspondence with Babbage. And in 1842, she was engaged to translate one of Charles Babbage's lectures on the analytical engine, which had been transcribed in French to English. And along with her translation, she included a huge number of notes, I think 13 notes and appendices. And among these was an algorithm for computing Bernoulli's numbers on the difference engine. And so far as we know, this was the first example of an algorithm being designed to be executed on a particular piece of general purpose computing hardware, which is a very long-winded way of saying it was software. It's the first piece of software that was ever written, so far as we know. The last piece that we need to put together this puzzle of modern computing is computing theory, computer science. There are so many people who made massive contributions to this, especially in the early 20th century. I cannot name them all, but some that jump to mind are Herman Hollerith, who developed the punched card tabulator and later went on to found IBM. Howard Aiken, who designed the Harvard Mark I, which is one of the first practical electronic computers. It's in the machine that Grace Hopper would develop the first code linker and compiler on. Konrad Zuse and John von Neumann, they both collaborated with and were inspired by Alan Turing, who I'm going to talk about now, to develop higher level models of computation. I'm focusing on Alan Turing specifically because this is a talk about pragmatism and the practicalities of writing software that does real world work. And the nexus of theory and practice is really what defined much of Turing's career. He was a brilliant theoretician, and yet he's most known for the practical applications of his work. Most of his work was kept secret until recent years. He was engaged in breaking codes for the British government during the Second World War. Turing's work helping to break the German naval Enigma, which was a incredibly sophisticated mechanical cryptography tool, which allowed the German Navy to coordinate their fleets secretly, required complex cryptanalysis and mechanical engineering, but it was able to eliminate an important advantage that the Germans had early on in the war. And after the war, Turing's work turned to a more general purpose computing applications. He worked on the automatic computing engine, which also remained secret for many, many years. He would later develop software and programming manuals for the experimental Manchester Mark I computer. And his early work on human-computer interaction led him to theorize about artificial intelligence and thinking machines in a way that would inspire later generations of computer scientists, some of whom are with us today. Stepping back a couple of years and coming across to my side of the pond, the war was still going on, and Americans were also developing electronic computing technology. And it's sad that so much of this period of computing history is tied up with war. But the United States was looking to make the calculation of ballistic tables more efficient. These are tables that were required for large guns, cannons, to calculate all of the different trajectories and settings that the gun required to hit a target at certain ranges. And all of these trajectories had to be computed by hand. And in fact, at this time, the word computer referred to a human being, usually a young woman recently graduated from college with a math degree. And they would sit in large rooms together and calculate and run these computations, these tedious, laborious calculations by hand. The result of this research and work was the ENIAC, which you can see part of. It was a massive, massive machine that filled a building, but you can see one of the programming switch panels here. The electronic numerical integrator and calculator, it didn't actually enter service until the war was already over. The hardware was a massive expansion in both the scope and the complexity from earlier electromechanical computers. But what I want to focus on is the software, because it's the software that's really interesting to me. Several of the women who had worked as human computers were engaged to program their replacement. And at this point, computer programs, to the extent that we can call them computer programs, were basically sequential algorithms. There were no standardized concepts for branching and flow control. That's not to say that branching and flow control didn't work, but it was very much defined by the hardware itself. So these 6 women that you see on the screen, Betty Jean Bardick, Betty Halberton, Marilyn Meltzer, Kay McNulty, Ruth Teitelbaum, Frances Spence, they were left to create the discipline of computer programming. And they had to invent concepts that are so fundamental that we would take them for granted. The idea of using breakpoints for debugging code was something that Betty Halberton came up with. Even the very idea of the if-then-else flow control pattern had to be invented. Later on, Bardick would be tasked with forming a team to convert the ENIAC to a stored program computer. So I mentioned that it very much depended on the wiring, and you saw the switch panel in the previous slide. The ENIAC was originally programmed by physically rewiring it. So you take the patch panels out, you would move the wires around to create new logic circuits, and that's how you would enter a program. It could take days or weeks to program the computer to run a computation. In a stored computer program, the code is stored on some storage medium. So you can think of paper tape, a punched card, a hard drive. So the idea was to convert the ENIAC to a stored program computer. This really pioneered the kind of framework of what we would recognize as a modern computer program. My last kind of media recommendation is unfortunately not available for free, but it can be rented for a fairly low cost, and I feel it goes to a good cause, is The Computers. It's a documentary that was produced by John Palfreman, Kathy Kleeman, and it was directed by Kate McMahon. This film explores in detail the pioneering work that these women and their colleagues did to really invent the craft of programming computers. And all of us who work in this industry owe a huge debt. So I highly recommend taking a couple of hours out of your life to learn about these absolutely amazing, brilliant programmers. Moving forward into the 1950s, we start to see the proliferation of modern high-level programming languages. So up to this point, programming, formal mathematics, and electrical engineering were all completely intertwined. Programming can computer without A pretty solid grasp of those other disciplines was almost impossible. A high-level language is meant to be accessible to people without a deep understanding of how the computer works internally. And that's not to say that, computer scientists writing C, that they don't understand how the computer works internally, but it's not necessary to know how the CPU is wired together. You don't need to understand it at that level. And this allows people to also write programs in languages that more closely match the way humans communicate with one another. In the early 1950s, Grace Hopper, who I mentioned earlier, had already done amazing pioneering work on the Harvard Mark I. She'd published a paper on code compilation and actually produced a working compiler that translated mathematical notation into machine instructions. This work on what was called the A0 compiler would influence a language called Phlomatic that she worked on, and that would lead to the development of the Cobalt language. At the same time, John Backus was working at IBM on a project to improve the experience of programming the new IBM 701 computer. And the result of this work was the first version of Fortran. These two languages represent a really important branch in computer science history. These early languages, Fortran and Cobalt, which, by the way, are both still very much in use today, 70 years later, are the ancestors of almost all modern programming languages. So if we look at this little bit of code, it's Fortran, it implements the FizzBuzz algorithm. We see a program that is fairly familiar to us. We see a lot of the early elements of syntax that would be inherited by later languages. We see statements that are terminated by Latin punctuation, in this case, semicolons. We see comment blocks. We see code that's structured into blocks. We see if-then-else logical structures and do loops. We jump forward another 10 years, we see languages like ALGOL with its function syntax, very familiar ways of passing and returning data. And then by 1970, we see a language that probably seems familiar to most of us, C, right? The PHP interpreter is implemented in C. If you've ever looked at any of the PHP internals, you've definitely seen it. And just looking at the syntax of this code, it's clearly very similar to PHP, and there's a good reason for that, which I'm going to come back to. First, I want to jump over to the other branch for a second and talk about Cobalt. So Cobalt is not a direct ancestor of PHP. The reason I talked about Fortran and ALGOL and C is because those are the direct ancestors of PHP. We can trace a line all the way back to 1950 to those languages. Cobalt grew out of a meeting that was organized in 1959 by Mary Hawes, who was a programmer for the Burroughs Corporation, who was a manufacturer of mainframes in the 1950s. This meeting included lots of folks from around the industry, including Grace Hopper. And the idea here was to create a language that resembled English and would allow non-mathematicians to create programs to execute business logic. Cobalt would put programming into the hands of people who were less interested in the computer itself, but rather in the applications. Software developers who could ignore the hardware, who could in fact write one set of source code that could then be compiled and run on many different pieces of hardware. Cobalt allowed for the creation of a new job, the Programmer Analyst, which is a title that is not seen very often anymore, certainly not outside of the mainframe world, but essentially is a person who uses computing technology and writes code to solve a business problem. And I think that that really describes what most of us do, what we call a software engineer in the mainframe world would have been called a programmer analyst. They solved real business problems and they wrote a lot of code. If you remember in the before time, in the long, long ago, when we used to travel all the time on airplanes, Cobalt remains an integral part of that experience. Cobalt calculates routes, it handles logistics, it manages ticketing, it drives the terminals that gate agents use to assist passengers. Without these computing systems, modern air travel just would not be possible. And yeah, we could replace and modernize all of that infrastructure, but it would be an unfathomable investment. So anytime you fly on a plane, praise Cobalt. And likewise, the banking industry adopted COBOL wholeheartedly. COBOL still manages accounts. It calculates interest. It settles transactions, powers bank tellers, both the human kind and the automated kind. So anytime you access your bank account or pay for something with a credit card, praise COBOL. COBOL, very much like PHP, was a victim of its own success. COBOL absolutely dominated the world of business mainframes because it was accessible to lots of people. It was easy to learn. It could be used to solve real business problems very quickly. Let's say you needed the computer to sum a ledger, apply a percentage-based adjustment, and then settle the transactions out to different accounts. This is work that would have traditionally been done by a bookkeeper, not by a mathematician or a physicist. COBOL allowed for programmer analysts, business people with tech skills, to create sophisticated business applications without having to have a deep understanding of computer science or electrical engineering or calculus. And when you have, big quotes, amateurs writing code who are more concerned with solving an immediate problem and less, or maybe not even at all concerned with writing good code, you get lots of spaghetti. So COBOL programs were notorious for having obnoxious variable names, control flows that were impossible to follow, indecipherable structure. They were brittle, they broke easily. Sometimes they produced completely inexplicable results. I don't know if this may sound familiar. This sounds like how people used to talk, and in a lot of cases still do talk about PHP. You know, the greatest weakness of PHP and of COBOL is the same thing that makes them strong. They get out of your way and they let you build an application that works. Now, it may not work well. It may be impossible to maintain. It could be fundamentally insecure, but it works. And working code can always be extended. It can always be improved. It can always be hardened and secured. Any business that relies on computers relies on working code. And that working code, no matter how bad it might be, is the most valuable asset that that company owns. In the 1980s, we saw computers reduce in price, specifically mid-range, which are large monolithic servers, like the System 38 mid-range computer that's here. We also started to see commodity computers and microcomputers, PCs, but now even racked servers, commodity racked servers would fall under that microcomputer label. This made computing much more available to businesses and even to hobbyists. By the 1990s, computers were starting to become a feature of the office, the home, school. And a new paradigm of computing was starting to emerge. Towards the end of 1990, Tim Berners-Lee, who was working at the CERN lab in Switzerland, had already started promoting HTTP within the institute. It's a subtle hint of things to come. One of the things that he did to goad people into using this new browser and web server was using it to host the phone directory, right? The phone directory is something that everyone needed to access pretty frequently. And by accessing the phone directly via this web browser, the user could avoid logging on to the mainframe. And in 1990, logging onto a mainframe required either having a dumb terminal or a terminal emulator software installed on a PC. Potentially, it meant having a token ring network card installed in your local machine. It wasn't necessarily the easiest thing to do. On August 6th, 1991, which was 30 years and a couple of weeks ago, Tim made his web server software and browser available. And it created a revolution. Very few technologies have been embraced so quickly and with so much excitement. A month later, the software had already been ported to the VM CMS operating system, which was the predominant operating system for IBM mainframes by a programmer, Louise Addis. And web servers started to come online at universities and research institutes around the world. By 1994, 3 years later, there were more than 2,500 websites. And by 1995, that number grew to more than 20,000. Some sites that would eventually become household names like eBay, Amazon, and Yahoo came online during this foundational period. It was quickly becoming clear that the static early web of handwritten HTML documents was insufficient. Individuals and soon after companies were eager to create a more dynamic experience for their websites. And since the only real contract in HTTP is that the client would make requests to the server using the HTTP protocol, and the server would return usually HTML. An obvious solution to the problem was to simply generate the HTML you needed on the fly in response to dynamic requests. This would also open up more sophisticated channels for two-way communication. Not only could a website be used to radiate information outward to clients, they could also be used to collect information from clients through contact forms and guest books. Powering these new dynamic web pages wasn't particularly simple. We again found ourselves in the same position of people wanting to solve real world problems, like receiving contact information from a user, taking an order. But to do that, you needed to know how to program a computer. There was an informal standard that was started by folks at the NCSA, that's the National Center for Supercomputing Applications in the United States, all the way back in 1993, for a gateway interface, essentially a standardized way of passing variable data into and out of a web server. This was later formalized by the CGI standard, the Common Gateway Interface Standard in 1997 by Rob McCool and John Frakes and Ari Luotanen and Tony Sanders and George Phillips. And to put this in context, much of the work that was happening on the web at this point was connecting legacy systems, mainframes, mid-range servers, databases, to web servers to make them accessible through a browser. And this standard was meant to provide a common way of building these gateways. Generally speaking, these gateways were written in the C language. And in fact, the RFC is largely specified in C. This was still very much a programmer-focused approach to building dynamic applications on the web. If you've ever done any non-trivial coding in C, you know that it's not approachable without understanding at least some computer science fundamentals. You have to manage memory. You have to buffer and secure data at all of the program's boundaries. You have to design and construct your own data structure and then compile your programs for the hardware that you intend to run them on. It's not exactly approachable to non-programmers. The CGI Perl module was an early attempt to open this kind of programming up to a much broader audience. So Perl is certainly a powerful programming language in its own right, but it's much more approachable with a smaller surface of pre-built data structures, built-in memory management. The interpreters are pre-compiled for lots of different machines and operating systems. And Perl was a tool that many system administrators and data analysts were already comfortable and familiar with, people that I refer to as being programmer adjacent, folks who use code in their day-to-day lives to solve problems, but who are not necessarily software engineers in the same way that people who are building complex applications are. But we were still very much in a C world and increasingly trying to plaster an HTML interface on top of it. CGI, whether it was written in C or Perl or any other language, was pretty clunky. Then along came Rasmus Lerdorf. Sorry, that's the wrong picture. Rasmus is a programmer and a systems engineer. And during these very early days of the web, he was a contributor to the Apache HTTP project. He was an early adopter of the web, particularly creating dynamic web pages. And he had been building a suite of tools to expose common functionality to the CGI interface. He was building what he called a C API for the web. So in 1995, actually, let's have a nice picture of Rasmus. He's actually a very nice, funny guy. In 1995, he shared a first version of his personal homepage tools, which he described as a small set of CGI binaries written in C. Keep in mind, at this point, there is no talk of a programming language. PHP is a C API for the web, a collection of useful CGI binaries. Not even a thought that this would become a proper programming language, but we will come back to that. So first, let's look at a web application from a very basic perspective. We have four principal concerns: the operating system, the web server, the business logic, and the data store. All dynamic web applications combine these four concerns together to solve a problem in the real world. And to accomplish this, we route each request through a stepped process. First, we receive a request in the form of a hopefully valid HTTP request. That request gets routed at this point. It could be routed to a static HTML file. It could be routed to a program or a script that will generate HTML. We'll assume the latter because we're talking about dynamic web applications. So at this point, we pass control over to that program. We execute it. Thanks to the CGI specification, we know exactly what data will be passed to the program and how it will be passed. The program executes, produces some output, hopefully valid HTML or some format that the client is expecting, which we capture. And then finally, the web server returns that output back to the client over the network, packaged up as an HTTP response. So all of this works great when you're hosting a single application on a server. But again, requiring a server and a network connection and the domain name and assigned IP address that those things require, we're far out of the hands of the typical person who wanted to share something about themselves or maybe run a small online store. Ideally, we would want to be able to share one server among a bunch of web pages. It's sufficient, right? You don't want to pay for a whole server to host one small website that doesn't get much traffic. If you can host multiple sites on a server, it makes financial sense for people who do own servers to rent out little bits of it. But this runs into a huge problem. If you're going to host web applications written in C, they will certainly be fast, but they could have memory leaks. And because all of the websites are running in a single Apache server, remember, this is before virtualization was a common thing, there's no way to make sure that one tenant doesn't access data belonging to another tenant or bring the entire server down, making all of their tenants inaccessible. We can use CGI PM, the CGI module for Perl, which makes it a bit easier to host lots of sites on a single server without having to worry about memory and crashes. But Perl is relatively slow to execute and hard to secure. Again, everything is being run under the same user. So this is where we come to PHP and what made it so incredibly different. PHP provided three key features that made it the natural choice for hosting multiple websites in a single web server. It is robust, efficient, and secure. And I know what you're thinking. That sounds like the exact opposite of what everyone says about PHP, but I want you to stay with me here. Perl CGI programs were very slow because Apache had to hand everything off to the Perl interpreter, which had to be started, execute, return. Mod PHP, on the other hand, pulled PHP directly into the Apache server. For PHP, you would pass control to a standalone fork. It executes and then terminates. There's no shared memory. There's no stored state. It was a perfect sandbox. Eventually, there would be an Apache mod for Perl, but even then, the difference in philosophy gave PHP a distinct edge. PHP implemented just enough of the Apache mod interface to handle HTTP requests. Remember, PHP is not a whole complete programming language. It's a tool to expose C API to the web. Mod PHP implemented the entirety of the Apache mod API. So mod Perl sites were much harder to secure and keep safe. PHP sites were safer and more secure because of the simplicity of mod PHP. Because PHP only needed to be handed over to a standalone fork, Apache didn't need to wait for an entire interpreter to spin up for each request, which allowed more sites to be served without requiring additional CPUs. And because everything is running in the same server, under the same user, a memory leak or infinite loop could crash the entire server. PHP avoids this by very simply just setting an upper memory limit. If the program hits that limit, it gets killed. The same approach works with an execution time limit. If you have a runaway loop, the PHP binary will stop. Even safe mode, which is one of those things that PHP has never really been able to live down, played an important role here. Everything was running under the same system user. Locking down access to system resources was incredibly difficult. I cannot, in good faith, argue that safe mode was a good solution, but it was a solution. To hate on safe mode in the context that it was created is to make fun of someone for blocking a door with a chair because the door doesn't have a lock. Safe mode allowed shared hosts to have at least some security against malicious code harming their servers. I'm going to offer you a really hot take here. PHP was never a bad programming language. At first, it wasn't even a programming language, but even when it started evolving in that direction, it wasn't bad. I'm going to walk through some of the most derided features of early PHP to try and understand them in the context of the time they existed. So PHP handles globals in a really weird way. You have a global statement to explicitly mark a variable as global, or you can put them in the $globals array, which looks like the CGI data arrays that come in from Apache, but are not. It's not that. In most languages, variable scope is just a matter of where the variable is declared, which is great and makes a ton of sense. But if you've ever been in the position of trying to find a global variable collision in a large and complex code base, it's kind of a nightmare. And explicit global declarations are a very simple way to avoid accidentally defining a variable as global. And Rasmus has talked, very openly about his experience being in exactly that kind of a situation is what led him to want to make sure that no one would ever unintentionally clobber a global variable in PHP. So what about register globals? This is another area where PHP was built to be simple and approachable rather than write. If you have a field on your web page called name, you have a variable in your script called name. It's hard for those of us who are programmers to understand this really, but for non-programmers, two of the hardest concepts to understand are scope and assignment. If you're building a set of tools to simplify creating dynamic web pages, this really makes sense. And regardless, these were deprecated a decade ago, so I don't know why we still hear about them. When these were introduced, the web was a very different place. JavaScript was created the same year as PHP, but it wasn't much used until Firefox came out in 2004. And even then, it was a few years before you saw widespread adoption of it. In the early days of PHP, there was no cross-site scripting to worry about. It was a very different landscape in which a feature like this existed. Magic quotes were never a good idea. They probably did more to cement bad practices in new programmers than they ever did to prevent SQL injection, but they were a solution, a very naive one, to a real problem that amateur programmers would probably have ignored no matter what. People talk about types in PHP, and there is nothing inherently inconsistent about PHP's type system. It all makes complete sense. It is well documented in the manual. Part of becoming proficient with a language is learning the types. With a strictly typed system, you have to learn lots of specific types. And with a weakly typed system, you have to learn the type conversion table. So in my opinion, sorry, I get heated about this. If you can be expected to remember the difference between all of C's types and type aliases, you can remember how strings are cast to numbers, or you can read about it in the manual, right? So haters, they don't get this one. PHP types are fine. They're fine. It's fine. They're fine. Let's move on. Function names are not case sensitive, and probably they should be. But again, let's talk about the context. PHP was used mostly for templating, and the web had not standardized on lowercase for HTML yet. So it made sense for people to be able to use the same standard for the PHP as for the HTML it was embedded in. By the time there was really a standard in place, changing this would have been a compatibility nightmare, and now we're kind of stuck with it. But we have tools. We have PHP CS. It's fine. People say that naming should be consistent, and sure, okay, please show me a language where that's the case. I've been doing this for 25 years and I've written production code in 24 languages. I'm not buying it. What people actually mean is that naming should be consistent horizontally across the surface of a language's standard library. And sure, if you look at PHP without knowing better, the function signatures are all over the place. The thing is, PHP doesn't have a standard library. It does, but it doesn't. PHP wasn't originally meant to be a language. It was meant to be a C API for the web. So you get ready. I'm going to blow your mind, unless you already knew this. The functions are just thin wrappers of the underlying C libraries. The string functions in libc were haystack needle, so PHP is haystack needle. The array functions were needle haystack, so the PHP functions are needle haystack. They're all perfectly consistent. They're just consistent vertically down to the libraries that they're wrapping. The real thing that I want to get to is who PHP is for. The web that PHP was born into was a very different place from today. A company might have a website, but we were still a very long way off from companies that are websites. Today, we're building more and more complex applications on top of the web, and that requires us to build more and more complex languages. We see it in the continuing evolution of PHP over the years, and also in the evolution of JavaScript. Both of these languages are having to mature as the demands that we place on them get bigger. But in 1995, the web was a much less complicated vehicle for expression, sharing art and research, to share information with a community, to share a small business. PHP was a custom fit for the shared hosting model of the 90s. That's why WordPress and Drupal were written in PHP, not in C or Perl. It's why they continue to dominate the web even today. 2 out of every 5 websites on the planet are WordPress sites. If you only count sites that are driven by some kind of CMS, it's 3 out of 5. It is absolutely no coincidence that the same people who hate PHP hate WordPress and vice versa. They can be very rough tools, but they can also be used to create incredible things or to hack something good enough to solve a problem for the moment. PHP didn't start out as a programming language. Rasmus in 1995 would have looked at you cross-eyed if you suggested such a thing. And I don't know, he might still look at you cross-eyed if you suggested it now. PHP became a programming language as the people who were using it to solve problems found themselves solving ever more complex ones. The problems evolved, and so the tool had to evolve. You think about where we started in 1995, a set of CGI binaries to process forms, no real math functions, you couldn't even loop. It wasn't until the second major version that we had a full set of flow control tools. Zev and Andy eventually stepped in, they created a real parser. We're starting to see this transition phase between a templating system into a simple programming language. With version 4, there's a new engine. I feel like this is where you can first start to call PHP a real language. Eventually, you didn't even need to execute it from inside of a web request. At 9 years old, we first start to see PHP take the shape that it would eventually take. So if PHP 3 was the childhood and PHP 4 was the awkward teen years, PHP 5 is when the show moves to college. PHP 5 has a cool car, a denim jacket, smokes cigarettes on the quad. A year later, PHP finally got a standard abstraction over many of the C database libraries that were available at the time. We started to move past simple websites. JavaScript was becoming a real player. APIs were needed to handle asynchronous requests. And nearly 15 years into its life, PHP was on the verge of a whole new evolution. So PHP 6 would have real namespaces, it would have closures, it would have better garbage collection, late static binding, native Unicode support. And that last part didn't work out really well, but all of that other cool stuff became PHP 5.3. And then a few years later, PHP 5.4, which I personally consider the first good version of PHP, finally got rid of lots of ancient cruft like register globals and safe mode. You know, the stuff that people are still talking about when they criticize PHP, they've been gone since 2012. They've been gone for almost a decade. With 5.5, we start to see influence from other languages like Python come in. We get big performance improvements. 5.6 continues to refine the type system, and then another evolution, version 7, built on a new engine, even more improvements to the type system, much better performance, a real AST that unlocked better developer tooling like static analysis. The whole 7.0 lineage continuously added more and more improvements to the type system, better compiler optimizations, and improvements to the op cache, all of which continue into the current generation. To think that in 25 years, PHP went from a thin wrapper over libc functions to a programming language and a runtime with a just-in-time compiler, and in a few months, version 8.1 will actually bring fibers, like actual native threading to PHP. And talk about coming full circle. Telling a story like this, one that spans now more than a quarter century, is really difficult. Today and tomorrow, we're going to hear from a lot of brilliant people. We're going to learn about the technical details of where PHP is and where it's going. We're going to learn how to optimize our code and optimize our teams, maybe optimize ourselves. Just like PHP has come a long way from being a simple tool, we've come a long way from building simple websites. Tools are funny things. They're often not beautiful things. Form will always be more important than function when you're creating a tool, after all. A lot of times, it's hard to even figure out what the function is. But as craftspeople, we grow with our tools, and they grow with us. At first, we fight with them, but in time, they become extensions of us. The simple bronze and iron tools of a 6th century mason don't really look like much. there's probably a better version of each and every one of them. There may have been a better version of each and every one of them in the 6th century. But in the right hands, they can build wonders that stand for millennia. PHP in the end isn't good or bad. It's a tool. It's a useful one, definitely a powerful one. And looking at PHP 8, we might even say it's a sharply honed and beautiful one in its own right. But it's never the tool that matters. Even the simplest tools can be used to build amazing things. The last year and a half have been difficult. It's still difficult. I mentioned before I had planned to be with you all today in person before we started having another bad COVID surge here in the United States, and particularly in the part of New York City where I live. We've all lost so much and so many people since the start of 2020, but it is a gift to be here together today, even for me being here digitally. During the pandemic, I know I've personally learned again how important community is. And what gives me hope and makes me excited for the future is the potential for all that we can build together. So today and tomorrow, enjoy this amazing gift of being with each other and learning together, because we have so much more yet to do. Thank you so much for your time.